Today, I want to talk about lengths of circular arcs and areas of circular sectors that correspond to some angle theta. So I'm going to have some circle. Its radius will be r. I'm not specifying that at the moment. I'm going to draw in an angle theta, and I'd like to know what is the length along the circle that goes with that angle theta. It's traditional to use a lowercase cursive s for this, so that's what I'll use too. If you look at that same general setup, but think about the area of the sector of a circle, I'd like to figure out a formula for that area as well. So S is going to be length along the arc of the circle, the arc length, and A is going to be the area of the corresponding sector. A circle is the most perfectly symmetrical geometric figure that there is. If you give me theta degrees, there's going to be a certain amount of arc length to go with it. If the angle were increased to 2 times theta by slapping a duplicate of the first one onto the picture, the amount of length that I've got will be twice as big as it was previously. If I have 3 of these things, then the length is going to be 3 times the original length. If you say, for instance, triple the angle, you also triple the length. This means that the length is going to be proportional to the angle. By which I mean the length is some number, which I'm going to call k, times the angle, and k doesn't depend on the angle itself. If you think about having a full circle, if you go all the way around, you will have 360 degrees for the theta. Also, the length completely around a circle is 2 pi times its radius. So keeping those two facts in mind, it must be true that 2 pi times r is this constant k times 360 degrees, which means the constant is 2 pi over 360 times r. You can cancel a factor of 2 out and find out the k is pi over 180 degrees multiplied by the radius of the circle. So the length along the edge, the arc length, s, is this constant, pi over 180 degrees times r, multiplied by the angle theta expressed in degrees. As an example, the equator of the Earth, roughly speaking, is a circle with a radius about 4,000 miles. If you have a central angle of 1 degree, how much distance does that correspond to along the surface of the Earth? Since we have our formula for the arc length, this is easy. The length is pi over 180 times the radius times the number of degrees. Pi over 180 times 4,000 times 1 in this case. I used my calculator and found out that this is about 69.813 miles. So if you're looking at, say, the position of the moon above the horizon, if you wanted to shift its position by about 1 degree, you would have to move about 70 miles. We'll figure out the area of the sector in exactly the same way. The area is proportional to the angle for the same reason that the arc length was. So it should be true that the area is some constant times the angle, and we're measuring our angles in degrees at the moment. If you had a full circle, theta would be 360 degrees. Also, the area of a circle is pi times the square of the radius. So knowing that particular theta and area value says that pi times r squared must be k times 360. which says that k is pi divided by 360 times r squared. The area of one of these circular sectors is pi divided by 360 times the square of the radius of the circle times the number of degrees that you've got. If I think about a 1 degree angle centered at the center of the Earth, traveling out to the surface, and I want to know what its area is, we now know the formula that lets us figure this out is going to be pi over 360 times the square of the radius times 1 degree. And again, using my calculator, I find out that it's 139,626.34 square miles. I just chopped it off after the 3-4. So to summarize what we've just figured out, if you tell me the radius and how many degrees that central angle theta has in it, I can calculate the length along the curve, or I can calculate the area of the corresponding sectors. Why are these numbers, pi over 180 and pi over 360 there? Basically, that comes from the fact that the usual angle units we use are degrees, and there is 360 degrees in a circle. If we were to use some other units, then the pi over 180 and the pi over 360 would still be constants, but they would be other numbers. There's a wide variety of applications in which you really wish that distance formula were simpler looking than it currently is. You'd like it to just be the radius times the angle, but you can't use degrees for that because we've already figured out what the formula for S is when you have theta in degrees. So instead of having 360 units in a full circle, units of angle that is, we're going to have 2 pi units in a new circle. If you sit down and redo the calculation to figure out what k is, k, if you're using these new units, just turns out to be r, and that means that the arc length is just r times the angle, except we're not using degrees anymore, we're using some other units for the angles. The name given to these new units is Radian Measure, R-A-D-I-A-N, Radian Measure. There's 360 degrees in a full circle, and we're going to rig it so that there's 2 pi radians in that same circle. If you were to take this fact and divide both sides by 360, you would find out that 1 degree is the same as 360th of 2 pi. And if you cancel a common factor of 2 out, you find out that 1 degree is pi over 180 radians. Now, pi is about 3, and 180 is a lot bigger than that. So 1 degree is only about 0.01745 radians. On the other hand, if you took this same fact and divided both sides by 2 pi, you'll find out that 1 radian is 180 over pi degrees. And if you do this on your calculator, you'll find out that 1 radian is about 57.3 degrees, roughly speaking. Knowing those facts makes it easy to convert from one unit to the other. Suppose you had an angle of 30 degrees. That's 30 times 1 degree, and 1 degree is pi over 180 radians. This has a factor of 30 in it. Cancel that out, and you find out that 30 degrees is pi over 6 radians. Likewise, 45 degrees is 45 times 1 degree. Do the arithmetic. 45 degrees is pi over 4 radians. 90 degrees ends up being pi over 2 radians. These are some of our commonly seen angles. If you have an angle that's not one of those, you might convert it to decimal. For example, 28 degrees is 28 times pi over 180 radians. Do that on your calculator, it's about 0.4887 radians. On the other hand, 139 degrees is 139 times 1 degree, and 1 degree is pi over 180 radians. Do the arithmetic, and you find out that an angle of 139 degrees in radian measure is 2.426. You can do it the other way as well. An angle that has pi over 3 radians in it has, since each radian is 180 over pi degrees, cancel out the 3. You find out that pi over 3 radians is 60 degrees. Pi radians, done in the same way, is 180 degrees. Pi over 5 radians works out to be 36 degrees. And a less nice number, 2.47 radians, works out to be 141.5206 degrees. There's one other concept that I at least want to mention here called angular velocity. The idea is you've got some object moving around in a circle, and you're going to have something that's kind of similar to the idea of speed, but it has to do with angles instead of distances. So the angular velocity, which people usually use the Greek letter omega for, is the change in angle divided by the change in time. The Earth, for example, does one complete revolution in 24 hours. If you wanted to use degrees for your units, then omega would be 360 degrees over 24 hours, which would be a 15 degree per hour change. On the other hand, if you wanted to use radians, then omega would be 2 pi radians over 24 hours, which when you do the arithmetic is about 0.2618 radians per hour. I'm just going to state this without any proof because it's easy. Speed is distance divided by time, so that would be 2 pi times the radius over time. Rearrange it so that it's in terms of omega, and then you get what you want. If you have an object moving around in a circle with some angular velocity omega measured in radians now, that's important. Otherwise, you're going to have one of those pi over 180 factors running around. If you're going around in a circle of radius r with angular velocity omega radians per whatever your units of time are, the speed is just r times omega. The reason that this formula is simple looking is, excuse me, we've chosen our units of measurement to make the connection between the angle and the distance very simple. As an example, radius has 4,000 miles. Omega, Earth takes 24 hours to go completely around once. So omega is going to be 2 pi radians over 24 hours. According to this claim, the speed of a point on the equator is going to be 4,000 times 2 pi over 24, which works out to be just a little bit more than 1,047 miles per hour. That's how fast a point on the equator is moving with respect to the center of the Earth. There's a calculator issue that you need to be aware of also. We have figured out some of the trig functions for certain angles. We figured out that sine of 30 degrees is 1/2. Sine of 30 degrees is 0.5. When we first started talking about this material, we had the mode button to look at. And if you'll look, degree is highlighted. That tells the calculator whenever I feed an angle into one of the trig functions, I mean that many degrees. But you'll also notice I could be using radians too. So if I go down here to radian and press enter, this unhighlights the degree setting and highlights the radian setting. Now the calculator is going to think that when I say sine of some number, that I'm talking about radians and not degrees. So let me get out of this. I'm going to calculate sine of 30 again, but what I get back bears no resemblance to 0.5. It's because I'm talking about sine of 30 radians now, not 30 degrees. So when you're working a problem and you need to evaluate the trig functions for various angles, if your angles are in degrees, make sure that your calculator is set that way too. And if it's radians, needs to be set in radians. Failure to do this will cause comparisons between 0.5 and negative 0.9, and that's very mysterious. This is a common mistake that people make, so don't fall for that. Usually when I'm working a problem that has trig functions in it, I check the setting every time to make sure it's the way I want it to be. This is about all I'm going to say about this part. In the next discussion, we will have one more way of thinking about trig functions. It's basically the same as two of the methods we've already looked at, but it's called the unit circle method. After we do that, in our remaining time, we need to talk about some properties of these trig functions. We need to look at their graphs. We need to look at, excuse me, we need to look at some relationships between these various trig functions. In the meantime, I hope nobody's caught the COVID-19 virus. I just have a dry throat today. And we'll talk about some stuff in the next meeting.